In chapter 13, we're going to talk about properties of solutions. So, the solution process is the first topic that we'll introduce here. And we should note, by definition, a solution is a homogeneous mixture of two or more pure substances. So, that can be any combination of a solid dissolved in a liquid, two liquids dissolved, two gases, or more. So any combination of pure substances that forms a homogeneous mixture. So that just means that it looks consistent throughout. So when we talk about a solution, we want to indicate that the solute, so what's being dissolved, is dispersed uniformly. So that's why everything looks the same throughout. So if you take powdered iced tea and dissolve that in water, for example, generally it is uniformly dispersed in the solvent, which would be water. And the solute then would be the iced tea mix. So let's talk about the ability of substances to form solutions. So I mentioned that it could be any phase of matter, any combination of phases as well. And really, it just depends on two main things here. So the natural tendency towards mixing, and we can think of things mixing together as an increase in entropy. So the disorder or chaos. So when we increase entropy here, that happens during this tendency of mixing. And we also want to consider what are called intermolecular forces. So these are forces between similar molecules or different molecules. And we're going to introduce these intermolecular forces right here. So notice there are four different interactions, four different intermolecular forces listed here. And they're listed from left to right in order of increasing energy. So these dispersion forces seen here, these interactions shown by these red dotted lines here, these would be the weakest type of interaction amongst the intermolecular forces. And all molecules have these dispersion forces. So all molecules will have these. And we can see that things that are composed of carbon and hydrogen. So the black is the carbon, and then we have just hydrogens here in both heptane and pentane. And that's referenced as well down here in the chemical formula. Um, Even non-polar bonds, so all molecules, specifically those that are non-polar, will have these dispersion forces, but also the polar types of molecules, such as we see here, that have dipole-dipole interactions, also will have those dispersion forces. So each type of force before that is indicated as we move up in energy. So dipole-dipole interactions will also have dispersion. So let's talk about, we see acetone here, which has this, what we call dipole moment or polar bond, which the negative end is over here. So we point the head towards the more electronegative portion. Then we see chloroform here, which is also a polar compound. The positive end is near the hydrogen atom right there. So both of these molecules, acetone and chloroform, are both polar compounds, polar molecules. And when they're next to one another, we would see these dipole-dipole interactions because each of these are considered a dipole. And this can be between like molecules or unlike molecules, like we see here. Acetone and chloroform are not the same. Then we have the highest energy interaction here, the hydrogen bonding. And it's called bonding, but it's just, again, these intermolecular interactions that are outlined right here. And notice that we can see this OH portion here. So that's this part of the ethanol. And the hydrogen So the delta positive portion is pointed towards the oxygen, which has some lone pairs here on water. So we see that positive and negative attraction, just like in the dipole-dipole interaction. But now with OH and NH, and if we had hydrofluoric acid and HF bonds, these are so different, these atoms in electronegativity, that they have this special super strong dipole-dipole interaction that we call a hydrogen bond. So again, only these three types of bonds can exhibit hydrogen bonding. And then that brings us to our highest energy interactive force here. So we have water molecules, which we oriented their dipole a short while ago. So the negative end is pointing in of all these water molecules here as they surround this sodium atom. So the sodium is an ion rather. The sodium ion is positively charged, so the negative end of all the water molecules are pointing around that positive and negative attraction here. And this is called an ion dipole interaction. So whenever we see ionic forces, we know that those would be the highest in energy here. So now that we know all the types of intermolecular forces, let's think about there's three types here of intermolecular interactions that are involved in solution formation. So first we have the solute-solute interaction. So say it's a salt or an ionic compound, right? So we have that crystal lattice type of structure here. So the solute has to overcome these interactions amongst itself and then be able to be dispersed in the solvent. And the solvent right here, that's attracted to itself, right? Like dissolves like. So water molecules would be attracted to water molecules, ethanol to ethanol, and like so. So whatever your solvent is, that needs to overcome its own interactions, intermolecular interactions, to make room for the solute. And then once that happens, there's also solvent-solute interactions, and this occurs as the particles begin to mix. So we can see this illustrated here. And again, the example used is table salt, sodium chloride. So that's the crystal that we see here. So chlorine's the green, sodium's the purple. As the water molecules surround the salt crystal here, you can see that eventually the water molecules will make room, orient themselves in a certain way, and then start pulling away, in this case, the sodium atoms. But we can also see over here the chloride. So sodium ions rather, and chloride ions. And then we can see this kind of blown up image down here of what happens when they become hydrated. And we're going to learn another term called solvation, where when these ions are solvated, they are surrounded by the solvent. And this is what ions being hydrated in solution would look like graphically. So let's continue here just to kind of summarize what we talked about so far. How does a solution form? So a solution will form as the solvent pulls the solute apart and then solvates them. So that's what we saw with the water surrounding the sodium and the chloride ions. We talked about the three types of interactions that had to happen, the three types of intermolecular forces. So separation of the solute particles, this will be an energy change that occurs to make this solution form. And then we have the separation of the solvent. So the solvent makes room, and then those new interactions that occur between the solute and the solvent. So we can see down here this graphic representation of the different energies, the different enthalpy values. So generally as our solvent, separates, makes room, and as our solute is separated, those are generally endothermic processes where we have to put a positive amount of heat in. And we see that over here as well. So both of these indicate that, and this is the sum of those two heat values, those enthalpy terms, and due to Hess's law, we can add them together like so. But then this process of mixing, as mentioned before, increases the entropy or the chaos, the disorder of our system so much that we actually can see an exothermic solution process over here upon mixing. And even this endothermic solution process shown over here, where we would have a positive delta H versus the negative delta H over here in the exothermic process, this still happens. So we might ask ourselves, why does that happen? Because we know that things don't just occur spontaneously without any outside intervention, with an endothermic process. But we do know that dissolving will happen for this specific salt here, this ammonium nitrate, in water when heat is absorbed. So we add heat, so it's a positive delta H, an endothermic process. But we still see this dissolve happen. And again, that's because of the increase in entropy will still favor this process because solution formation is much more disordered. And we can remind ourselves that just because a substance disappears or we can't see it anymore when it comes in contact with a solvent, doesn't mean that it dissolved. It may have dissolved and just, gone from being a solid to an ion, but it also may have reacted. So sometimes we see color change or what appears to be dissolution. But we can tell the difference because dissolution is a physical change. So something dissolves, but it can be recovered. So we can get back or recover our solute if we evaporate our solvent. But if something reacts with the solvent that we think is just solvent, it's actually a reactant and we create something new. So we can't get back that original solute. So we'll continue with our discussion in the next section about saturated solutions and solubility.